Let's dive into the world of abstract algebra. Abstract algebra is the study of mathematical structures. Abstract algebra goes beyond just dealing with numbers. Instead, it explores algebraic structures and their fundamental properties. Think of it as a way to understand the rules that govern how things work in mathematics, not just the numbers themselves. Abstract algebra focuses on three key structures: groups, rings, and fields. Let's briefly describe each one. Groups involve one operation that follows rules like closure, associativity, having an identity, and inverses. Rings have two operations, addition and multiplication, with specific properties connecting them. Fields are a special kind of ring where every non-zero element can be inverted through multiplication. Let's discuss groups in more detail. For a set to be considered a group, it must satisfy four essential axioms. First, closure. For any two elements A and B in the group, when you perform the group's operation on them, the result must also be an element of the same group. Second, associativity. The order in which you group elements when performing the operation doesn't change the result. That is, a asterisk operator B, asterisk operator C equals a asterisk operator B asterisk operator C, for all A, B, C in the group. Third, identity. There must be an element in the group, often called E, such that when you operate with it on any other element, it leaves A unchanged. So E asterisk operator A equals A asterisk operator E equals A. Fourth, inverse. For every element A in the group, there must be another element, A inverse, such that when you operate A with A inverse, you get the identity element. Let's look at some examples of groups. The set of integers under addition, denoted as z+, forms a group. 0 is the identity element, and the inverse of any number is simply -a. Another example is the symmetries of a square. There are 8 transformations, which includes 4 rotations and 4 reflections that preserve the shape of the square. These transformations form a group under the operation of composition. Now let's talk about rings. Rings involves two operations working together. First, it forms an abelian group under addition, which means addition is commutative. Multiplication is associative and has closure property. Finally, multiplication distributes over addition. Now we come to fields, which are the most complete algebraic structure. A field is essentially a commutative ring where every non-zero element has a multiplicative inverse. This means you can divide by any non-zero element. Some examples of fields include rationals, reals, and complex numbers. You might be wondering, why should I study abstract algebra? Well, it has many real-world applications. For example, cryptography relies heavily on abstract algebra for creating secure encryption methods like RSA and elliptic curve cryptography. Abstract algebra is also used in crystallography to understand crystal structures and symmetries in materials science. So, abstract algebra is not just abstract. It is a powerful tool with practical uses. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.